Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. Sorry for the long time that has passed since my last video, but I was really busy with my final exams and other things and I couldn't get any time to record. Also, I've changed the setup a little bit so that everything in the board can be clearly read. I hope you like it. Today we're going to talk about velocity, both average and instantaneous, acceleration, and also we're going to do some exercises relating position, acceleration, and velocity. So let's start! We all know that velocity is the relationship between the distance we cover and the time in which we cover that distance. Let's examine velocity in a time interval such as t1 to t1 plus delta t. In an interval like this, average velocity is defined as displacement over that same time interval. To keep things simple, we're going to do the derivation in only one dimension, and therefore we're going to take delta r to be the change in position in the x direction I had. So this would be equal to delta x over delta t I had. Let's examine what this means geometrically. Okay, so if we have a graph, I'm going to draw over here, of time versus position, and we're going to have a curve on it, that's going to be the position over time of a particular object. And let's see if we have some times over here. We have t1 and t1 plus delta t. And this would be delta t, the time interval in which we are examining velocity. Accordingly, we're going to have some positions, x of t1 over here, and over here we're going to have x of t1 plus delta t. And the difference between these two positions would be our change in position. Therefore, we can see that by this definition, our average velocity would be the slope of the line joining these 2 points. Slope of this line. Let's make it a little bit shorter over there. Okay, but what if we want to know not the velocity over a long period of time, but the velocity at one specific point in time? To do so, we'll need to take smaller and smaller delta t's. We'll take it smaller time intervals. We'll take it over here, then over here, over here. And in the limit where delta t is almost 0, and we're taking 2 points almost at the same position than t1, we'll have this other line. Let's draw it in green over here. And instantaneous velocity would be the slope of the green line. Let's analyze this situation analytically. Taking smaller and smaller delta t's is equivalent to taking the limit. So instantaneous velocity equals the limit as delta t goes to 0, as we said before. Of what? The limit of average velocity. And this is equal to the limit as delta t goes to 0 of delta x over delta t. That seems like a 6, not a 0. Let's fix it. And if we expand this expression, the limit as delta t goes to 0, remember delta x is that difference, not delta over here, x of t1 plus delta t minus x of t1 over delta t, we realize this is the exact definition of a derivative, right? Therefore, this is going to be the x dt in the I direction. I forgot to write that vector. So, the derivative in the I of the position over time. And we can see that our two definitions are consistent with each other. Because if we remember, the geometrical definition of a derivative is the slope of a curve at a point, the slope of the tangent line to a curve at a point, a specific point. So these two definitions are consistent. If we want to generalize this to 3 dimensions, it could be done analytically with some more efforts. I'm just going to write the solution. We will get that velocity is the derivative of displacement, and expanding this would be the derivative of each of the components, derivative of x over dt in the y direction, y over dt in the y direction, and in the z direction too. And this would be our definition of velocity. Okay, so now let's deal with acceleration. We all know that acceleration is the relationship between the change in velocity and the time in which that change takes place. That's why our definition of acceleration is going to be pretty much the same one than what we did for velocity earlier. And therefore, we're only going to do it analytically this time, as the geometric definition is the exact same than the one we gave before. Let's analyze this in a particular time interval. So let's do it again in our time interval t1 to t1 plus delta t. And in this time interval, average acceleration is going to be defined as the change in velocity over the change in time. To keep it simple, once again, we're going to take delta b to be only in one dimension. We're going to take the x component. This is going to be defined delta bx, the I direction. And therefore, this is going to be equal to delta px over delta t in the I direction. Now, this notion of average acceleration is not going to be as used as that of average velocity, and it is much more interesting to analyze the notion of instantaneous acceleration. In the same way as we did before, instantaneous acceleration is going to be equal to the limit in which delta t goes to 0 of average acceleration. And this is going to be the limit in which delta t goes to 0 of delta bx over delta t in the I direction. Once again, if we expand this expression, we are going to have bx of t1 plus delta t minus bx of t1 over delta t in the I direction. This is going to be the definition of derivative. And therefore, this is going to be the dbx dt in the I direction. So that's how we define acceleration. If we want to generalize this definition to the 3 dimensions, we could do all the analysis, but I'm going to give you the answer. It will be that acceleration is equal to the derivative of velocity over time. And if we expand this vectorial expression, we'll have each of the components, and that is the x component in the I direction, the y component in the j direction, and the z component in the k direction. And that is how we define acceleration. Alright, now it's where the fun begins. Now that we have defined some of our most basic notions of position, velocity, acceleration, we can start doing some exercises. So let's try to find out all of these quantities, position, velocity, and acceleration, from this formula for position in the x direction. t squared, where we will take p to be a constant of a value, a positive value. Okay, so remember that our definition of velocity is the derivative of displacement over time. Therefore, velocity in this case, in which it's only one dimension, so we don't need to put the vector, it's going to be dx over dt. Or this is going to be d over dt of bt squared, and remember your derivatives, this is going to be 2bt. Similarly, find acceleration. This is going to be equal to the derivative velocity over time. Again, it's only one dimension, so no vectors. And this is the derivative of 2bt, and that is 2b. It's great. Now we have the acceleration and velocity of an object just from the position of the object through time, something that we can measure. Okay, so now let's do something a little bit more complicated. We're going to start with the acceleration. We're going to define it as a constant, a sub 0, and we're going to work backwards to find position and velocity from this acceleration. So to start, let's remember that acceleration is defined as the derivative of velocity over time. For this is equal to a sub 0. See that once again we are not dealing with vectors, we are just doing it in one dimension to keep it simple. Now, in a math class we would need to be more rigorous about what we are going to do now, but just assume you can do it. It can be easily proven. We're going to multiply through by this infinitesimal contribution dt, and we're going to get dv equals a sub 0 times dt. And once we are here, we can take integrals to both sides of the equation. In physics, all of your integrals are going to be definite integrals. You are dealing with situations in which you have specific variables, and therefore this is going to be we're going to find a t prime as our integration variable in this case, and this is going to be t prime from t prime equals to 0 to t prime equals to t. That's why, well, by defining t prime as our dummy variable, we can get t, and usual t we're used to, as the variable we're going to have after the integration. And similarly, this is going to be a b of 0, b prime, b of 0 equals b sub 0, the initial velocity our object has, and the upper limit going to be b prime of t equals b of t. Right? And if we carry out this integration, this is going to be b of t minus b sub 0 equals a sub 0 times t. And if you look closely, this is one of the formulas that are usually used in kinematics. It just came from the definition of acceleration. Now let's do the same for position. We know that velocity is defined as the change in position over the change in time. And this is going to be equal to all of this expression over here. That is b sub 0 plus a sub 0 t. Once again, we're going to multiply through dt. We're going to get dx over here. And it's going to be b sub 0 plus a sub 0 times t dt. Once again, we're going to do the integrals on both sides of the equations, and this is going to be from t prime equals 0. We're going to integrate from t prime, equals 0 to t prime equals t. And similarly, in this side of the equation, we're going to go from x of 0, x prime prime, equals x sub 0, so 0, and x prime of t equals x of t. Now, if we carry out this integration, we're going to need to separate those two sides over here. So t prime equals 0, prime equals t, v sub 0 dt, plus the acceleration part prime using the properties of integrals prime, I forgot about there. And if we carry out all of this integration, we will find out that x of t minus x sub 0 equals this contribution, that's v sub 0 t, plus 1/2 a sub 0 t squared. And if you look closely enough, you can find out this is once again one of the classic equations that are used in kinematics. So, oh, that's not a 2 right there. Let's write again that 1/2. And that is how you reach G position from acceleration. These are the most basic tools we will use on our kinematical analysis of classical mechanics. Remember that you can subscribe to the channel and press the bell so that you don't miss any of the videos. And also remember to press the like button if it was the case. I hope you liked it and see you another day with more Physicawesome!